Alright, let's get started on the second problem of the day. This is LeetCode number 437, path sum 3. Given the root of a binary tree and an integer target sum, return the number of paths where the sum of the values along the path equals target sum. The path does not need to start or end at the root or a leaf, but it must go downwards. So this is a different problem from path sum 2. We've added the additional complication. So this is from path sum 2. We don't just start at the root and at the leaf, but we keep the same number of nodes, or at least a similar number of nodes. Between 0 and 1,000 there are. So there's a pretty big chance that this will not be, it can't be backtracking. Because this usually requires some flavor of exponential time, which is way too slow for anything over about 10, right? So we don't want to do that. We don't want to do backtracking in this case, or at least in the way that it's traditionally used. Let's see, what else could we do? We could run maybe like a recursive solution. Pass in our current, or pass in two values, or sorry. Given a value input and our current node value. So this value input is from the parent, and our current node value, we can return the number, or return +1 if a path exists here. The question is, we have a lot of branches if we want to calculate every possibility, right? If we want to exhaust all possibilities here. The idea is that if we start with 10 and we go to this 5, we could either take this 10 or we could take this 5 as a starting point. In this case, it would either be 15 or just 5. However, when we go to this spot here, we need to either evaluate this as 15 or 5. And, well, does that actually cause an issue? Yes, because for each branch, well, for each node, we only create 2. Do we create 2 possibilities? Because it either must continue a branch, it must either continue the older branch or start anew. And so a potential idea then is to do that. We just pass in 2 potential candidates for each child. The problem is that that may be a little bit on the slow side as well. Let's see. So for example, we would pass in 5 and we pass in 15 to this 2. Because we don't know at the bottom whether or not there will be a negative number that could eat away at some of the excess amount over our target sum, right? So we had to pass in both values in a very similar way that we had to pass in the values with path sum 2. I'm just thinking if this is a viable solution or if there is something better that we could do. So we do this 10. We pass this on to this -3. This -3 has the opportunity of being a -3 or a +7. And so we pass both onto 11. And now this 11 has the possibility of being 3 things, right? It can be 11, it can be 8, or it could be 18. Okay, so we still have some exponential blowup. Previous to plus start current. Of course, this doesn't happen at the root level because, well, it just doesn't. Because we only have one parent. Well, does this get worse over time? Yes, it does. We sort of add a new layer every time, don't we? Because if we go down to this 2, or this 1 rather, we have a chance of doing 10, 5, 2, or 5, 2, or 2. Okay, so maybe it's not as bad as I thought. Because we sort of get rid of the branches in the middle in a sense, because we can't do any of the other branches without including the parent. Like we can't have like a permutation of this where we have only 10 and 2 and 1. We have to do 10, 5, 2, right? Or we do 5, 2, or we do 2, 1, right? So we could either choose to continue the old branch or we start a new one. But still that causes, I think, an exponential blowout because we still need to make 2 choices at each individual branch, if not 3, right? So this would be 2 to the n or 3 to the n because we branch out so much. We create 3 branches at each individual point. But do we? For each child, we create 3 additional possibilities from there. In this case, potentially there are some ways to alleviate this. It could be a Hashmap problem. We've seen examples where we add up or we've seen some clever solutions where we use the distance from, or you like combine segments with the same sum to produce an outcome. I can't remember exactly which questions they were, but they were the questions where, with regards to subarrays, where we had the same, was it the same sum? I don't think it was quite the same sum, but it was something very similar to that, I think, where we sort of calculated how many times we've encountered this particular value. And then if a particular value has been encountered before, then we can add it to our path and increment a value and be on our way. And this could also be a dynamic programming problem where we do some top-down or bottom-up dynamic programming in the sense that we cache something with regards to our previous solution. And if that were the case, I would probably be caching the previous value or the previous sum in, well, some manner, right? In order to get a better result. I'm just not exactly sure how I would do that. What if we, for each branch, we pass in a hash map that indicates all of the possible previous sums along with their frequency. So the idea is that when we go to 10, we pass this down to 5. Well, 5 doesn't have any complement within here. If our target sum is 8, 8 minus 5, there is no 3 within our hash map. We'll just add 5 into our hash map and pass it on to their children. This 3, however, knows that there is a target sum 8, and it knows that there is a 5 that exists within the hash map, and so it returns a 1. It also adds itself into the hash map and passes it on to its own children. On the flip side, this 2, well, this 2 knows that there is a 10, a 5, and a 15 in the solution, but there isn't a complement here. So it'll add itself. It'll also add 7, and it'll add 17, and it'll pass on to the next one. The problem is that then we sort of run into a problem where we kind of have a large amount of space used instead, which may or may not be necessarily the solution or the angle that we want to take. Because as these trees get longer, it can start to be a problem if we have to create a sum combination for each element within the hash map with our current value. That would be pretty bad, honestly. We could try that, though. Is there anything else that we are missing here? Well, how much would each individual size of that be? The hash map. The hash map can only be as large as, will always be 1 plus 2 plus 3 plus 4 plus 5 and so on until n, where n is the depth of our tree. So it'll always be the depth of the tree squared. That is the size of our hash map. And so the maximum space that this will take up will be also the depth of our tree, which is log base 2 of n squared. And so the maximum space in that case, assuming, so the maximum number of elements within that sum hash map is 1 plus 2 plus 3 plus 4 plus dot 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 plus n, which is n squared, where n is, or let's do O of h squared, where h is the height of the tree. And since the height of the tree is bounded by log base 2 of h, then the number of elements within the algorithm for the hash map is O of log base 2 of h, because this needs to repeat for each one, of h squared, which is O of h. Because the squared moves down. Does it? Man, it's been a while since I've done logarithms. I mean, to a certain extent, that's only one sort of. Let me think about this. Height of the current node. And if that's the height of the current node, then what happens when we apply it to the deepest element within the tree? Well, then that'll be log base 2 of h squared, right? I'm not too sure about this. And how about this? What about the time? Well, we would still, to calculate, or we need to find the number that matches and return the number of elements that it works with. So we added 10 here. We would add 5 and 15 here. Then we add 17 and 7 and 2 here. And what happens if we added something here? Then we would add 18. We'd add 8. We'd add 2. Or no, we'd add 3. And we'd add 1. So yeah, we add the height of the tree in terms of the number of nodes, or the number of values each time, if they don't already exist, in which case we just increment some value. And I think that's a decent enough solution that we can try to see if we can go ahead and code it. In finding the number of elements is like finding the element that works with it is in O1 time, because we're dealing with a hash map. But we still need to go through each element, which means O of n, where n is the number of elements within the tree. I think that's a decent enough solution. Just really curious. Number of nodes within the range of 0 to 1,000. I'm not sure that tells us that much. Only that maybe the solution is in some flavor of between linear and quadratic time. Maybe n log n, but how would n log n work? Honestly, not sure. Because you can't sort this. Maybe even in an array representation. What happens if you did it? If we knew about where the position of the children were, that let us cut it down, but would that really do much for us? Like, what good does it do for us if we had an array representation of this tree compared to a tree representation of the tree? I'm not sure if there really is any benefit to that. No, I can't really think of any good benefit to that. So let's go ahead and start coding. So create a, well, we create the helper function, right? We'll call this sum map, which will be a mutable map. Actually, it'll be a map of int to int. This will return an integer as well. This will be a non-nullable tree node root. And we'll say val complement is equal to target sum minus root dot val. If sum map dot contains complement, then sum map dot add let's see. We want to add or put or what is it? It was like, it's been a while since I've done this. I want to do a put or default. Or maybe it's a get or put. Oh, okay. Into here. I want to put into our complement the value, or we add in a 0 plus sum map get complement. And we know that it exists in here, but we'll also do a or default 1 0. So the idea is that if there exists a complement value within here, then we know that our, let's see, then we know that a path exists where we had some sort of complement before in a previous path coming up from the, or coming down from the root down our path. It may be multiple times that we've encountered this, but now we need to actually finish that path and get to our desired target sum value. So we may have encountered it multiple times. Maybe it's gone up and down, sort of like what we said with the other problems. And now with the addition of our value, we can create as many paths out of it as there have been times that we've encountered that complement value before. We will also add into our sum map, and then we will do let's see. If we have encountered our complement, do we want to continue forward? Yes, because there's a chance that it goes up and down and back to our complement value, right? So we need to continue, and we need to add in our number as well. We just need to make sure that we don't duplicate our values, essentially, by accidentally adding in another value of this complement. So we can do some map for each entry. And since this is a map, we kind of need to do a copy. And does the regular map allow for a copy? Let's see. We can do toMutableMap. And we want to put this into our copy, rather. We don't need you to be a getter. Well, you need to be a getter put, actually. You don't need to be a getter, or you don't need to be the copy. You need to be the copy. You need to be the copy. You need to be the copy. Actually, this is a perfect opportunity to just use this. And since this doesn't have our potential complement value, we are safe to add all values, right? Because the main worry is that, like, we added our complement value, like our sum, and then we add it again. So this way we kind of avoid it. So some map copy put into our, want to do a val new sum is going to be our current root value plus our entry value, entry key, right? The key is the actual value. The value is the frequency. So into our new sum value, sum map dot get our new sum value. Let's see. Do we want to do a get or put? I think we could do a get or put. And this, if it doesn't show up in our copy, then we can just use a 1 in there. Or 0 here, and then plus 1. There we go. And then, now we want to recurse on both the left and the right side with this new value, right? So now we want to say val left map is, or left amount is equal to path sum with our root.left, or if root.left is not null, first of all, then we want to try there, still pass in our target sum, and then we want to do our sum map copy dot to map else 0, and we want to do a very similar thing for right amount. And these are just the number of paths that happen on the left and the right side. And what we will return is, let's see, the current number of paths that end here. So this will be sum map copy dot get target sum, or 0, plus left amount plus right amount. So I think that works. The idea, again, is relatively straightforward, I think. We first check to see if we have a value that matches, right? So we take our target sum, we subtract the current amount, and we see if that we've ever encountered within our current path the value that we need. If that's the case, then we can start from whichever path it was, whichever node it was, and we can go all the way down to our current node. It's guaranteed that that each of these sums are coming from some predecessor. We don't know which one, but we know that it is some predecessor. So we will add the number of paths that come from our predecessor that add up to our complement amount, and that is the number of paths that we can create for each of those. Then, let's see. So actually, maybe we don't want to actually add it within here. Do we want to add it? We still need to add it within there. Then in that case, do we want to add our current amount or just the left and the right? I think it's just the left and the right. Because our left amount will also carry this sum map copy, which will have the number of let's see. Let me think about this. Val num paths terminating here is if sum map dot contains complement, then sum map get complement, else or 0, else 0. This is for sure non-null. We don't need this at all. So this is the number of paths terminating here with the left amount and right amount. Then we go through each of our entries and we add our current value on top of it. We should also add just our plain. We should also just add our plain copy, right? So if we were to start here, so sum map copy put into our root.val, our sum map get at our new or at our root val, or 0 plus 1. And we'll do this at the end. Actually, it doesn't matter if we do it at the beginning or the end, because we're moving it to a copy. So the idea is that we can start either at our current node, which is why we add this, can start a new path at our current node, and there's one path. If there is none before, there is now one path that creates this value. If not, then we will just increment the number of paths that can create this amount. Then for each other value within our original map, we will add our current value to it, and we will, after we've added this new amount to it, we will either add the previous number of paths that created this, or we will start it at 0 and then we will add 1 to it. So, get or 0. I think this is fine. Let's see. I think this is effectively the same thing as what we did before. Then we will recurse on both the left and the right if they exist with our new sum map and see the number of paths that they can create there that terminate there. So when we go to the right side here, it would take the same target sum 8, we'll subtract 5 and we'll see if 3 exists. It doesn't. So we just add 5 into our map. We will also go through and add 15 to our map. And then we will recurse on the left and the right with 5, 10, and 15. Then at 3 we know that 8 minus 3, we know that 5 exists within here. And so the number of paths terminating there is the number of paths that add up to 5, which is just 1. We add the 3 into here. We add 8, we add 18, and we add 3. Well, we added 3 before, so we add 8, we add 18 into the mix. So we had 5, 10, 15, and then now we added 3, we added 18, and then we need to add also our 15. No, sorry. Added that. We added that, and we need to add. We don't want to add 13 actually. Ooh, how do we avoid that? We don't want to add 13 to our list. We don't want to add 13 to our list, which means that we kind of need to only include. We kind of want to only include elements within the list that are additions, right? So we want to add 5, we want to add 10. Or we want to add 5, we want to add 15. We don't want to add 10. We don't want to add 10 because we can't just use 3 and 10. We want to add 5 and 15. I think we're already doing that, right? Here? Because we add the elements into here, and that's what we're passing in. We're not actually passing in 10. Here we're only passing in. Oh no, we are. Maybe we want to start this blank then. Int to int. And the idea is that we want to add in 5, we want to add in 10. We don't want to, or we want to add in 5, we want to add in 15. We do not want to add in 10. Here, so now we add in 3, we add in 8, and then we add in 18 into our map, and that's what we pass down to 3 and -2. We don't want to pass in 5 because we can't have 5 and individually. We don't want to pass in 10 for the same reason. Okay, so I think this works. Let's go ahead and return path sum on our root with a target sum and a mutable map of int, or just a Empty, can I do an empty map of int to int? And of course, if our root is null, then we just return null. Or 0, rather. Let's go ahead and run this and let's see if there are any issues here. Oh. Okay. Let's see. Looks like it works for the first one. Let's go ahead and try out this second example. Looks like it works for this one too. Exciting. Okay. Let's see if it works for all cases then, or all the test cases that LeetCode has. Looks like we ran into an edge case here if we had 1 and 1. Target sum minus root val. Let's see. Let me think about this. Is there any other case where this would be necessary? Or is it only on the root? If we had a target sum minus some amount of value, and if it starts here and it's the same amount, then we can end here. So if target sum is equal to root.val, if target sum root val 1 else 0, because we can always add another path. We could always add another path here if the value is the same as the target sum. So let's just make sure that this is a handled case now. So yeah, that was one of the edge cases that I didn't quite think about. Let's make sure that it didn't break anything. I don't think it will break anything, at least in the examples, because there aren't any situations where the target sum actually equals the... There aren't any situations within the initial examples where the target sum is equal to the actual value. Looks like we're off by 1 here. Let's see what's going on. Oh. So it's like this, and we wanted a value of 2. We're getting 14 rather than 13. Because there's a value of 0 here, and there's a 2 here. It seems like we're over-counting then. But where? So let's see. So the only thing that's really changed, and let's see if this was after. So this was at case 92, and this was at case 120. Okay, so this isn't caused by our change then, likely. This is probably something else. Let's see. It's hard to say because there are just so many cases that are possible. Line at, and let's do a root.val. there are, and that paths. Let's take a look. So at this 0 on, presumably all the way on the left, there is one path, so 1, 0, 1, 0. Then at this 1, there are 3 paths, so 1, 0, 1, 0, 1, 0, and 1, 1. So those are the 3 paths. So at this, and then at this -1, let's see, so 1 path, 2 paths, 3 paths, 4 paths. Then there's 5, 6, 7, 8. So let's see. At this 1, there are 5 paths. Is that correct? 1. So there's 1 all the way down. That's 1. Then there's 2, 3, 4. Where's the 5th path? Let's see. 1, 2, 3. Is there an issue there? Kind of want to cut this down and just check this out, this part out, because there's 1 path here, 2. Okay, I think that's actually fine. 1, 2, 3, 4. Sorry, I'm like confusing myself. No, I'm really not sure. If I did, let's just change these all to like 9s, because I don't care about them, but I need them to stay as they are. Oh, 1, 0, 1. I think this one? Nope. Previous. There you go. And you need to be turned into 9. Oh, no, not you. You. And this should still give me an issue. Why? But why though? At this one here, there are 3 paths. Oh, this is incorrect. This one on the left should be a 0. I think that's how it was initially set up. Okay. And we were off by 1. Correct. At 1, 0, 1, 0, there is 1 path. Correct. At this 1, there are 3 paths. 1 and 2. Where's the 3rd path? If we wanted a target sum of 2, minus 1. There are two ways of getting... Okay. Very confusing. Not sure where they're getting their values from. Sorry, I'm just messing around with the tree visualizer, so in the hopes that it would have made it easier, but now I screwed up the tree, so let's just do that instead. There are 3 paths here. How can there be 3 paths at this one on the right? It is true that there are 3 paths here, that there is 1 path here, but it is not true that there are 3 paths here. There should only be 2. Perhaps I am adding something here. We can add, or we can start our new path here at this current node. That is true. And then for each value within this entry, within 1 and 0, there are 3 paths. Very interesting. There's no left and there's no right, which means that the only thing that could happen is the num paths terminating here calculation is too high. Well, does 1 contain 1? Well, 1 contains 2 1s, actually. Does it? It only contains 1 1, or at least it should. Well, 1 and 2. That's fine. Where's the third one coming from? Let's take a look. Because there's definitely something to do with the map that's wrong. With the... Okay, so this... There are 3 instances. Okay. Current map is nothing. Then we go 1 1, and then 0 1 1 1. And that's fine. Then there are let's see. There's 1 instance on once we go here on the left. There should be, let's see, 1 instance of getting to 1. No, 2 instances of getting to 1. And 1 instance of getting to 2. No, we are going all the way down. So in that case, there is 1 instance of getting to 2. 1 instance of getting to 1. Why are they adding up? And there should be no instant... Yeah. There's 3? How are there 3 ways of getting to 1? So our map is incorrect. We go through each map entry. There's one way to get to 0, one way to get to 1. That is correct. But something breaks here where we go through this one. When we process this node right here, we go through 0 plus 1, that's one way to get 1. And then 1 plus 1, that's a way to get to 2. And there's 2 ways to get to 1. And there should be only 2 ways to get to 1 from there. Let's see. But when we add it up, let's see. Seems like we're adding a way to get to 2, or adding a way to get to 1, and adding a way to get to 1 again. So we added our own value to get to 1 here. We added a way to get to 1 via the 0. Where's the other one coming from? Just really overall confused about this. It's got to be like some small issue. Let's see. So we add 0, 1, and 1. There's one way to get to 2. Let's see, adding 0 is equal to 1 and 1. That adds 1 here. Does that shouldn't, that adds a 2. And that should be it. Very, very confused. I hate just doing this like print line debugging stuff, but genuinely can't just pinpoint it down. Oh, whoops. So when we add 0 is equal to 1 and 1. Let's see. Let's see. Because there was one way to get to here before. There was one way to get to 1 before, and now there's 2 ways to get to 1. So maybe if is not equal to root val, then we do that. I think that fixes it, but I'm not happy about it. Because I feel like there are probably holes within this logic itself. It's not quite, yeah. Now we're undercounting. So this isn't quite what we want. We do know that there should be an extra value in there that we can start a new path at our current node, but we don't want to accidentally overlap with it. Now we're undercounting. Let's see. Let's see where we are undercounting then. Don't need this. We just need to take a look at sort of the here. So there's one path here. There are two paths here, correct? And there are four paths here. 1, 2, 3. Well, there's two from here. Or one from here, two from here, and then one that terminates here. Yes, that's correct. Then there's one, -1. There should be one path here. Yes. There is no path here. At 0, there are 1 paths. Where does that path come from? Oh, 0 to 0, yes. Okay, there is one path, yes. And then at 2, there are 4 paths. There is 1, 2, 3 that starts here, and 4. Okay. Then at this -1, there are no paths, correct? There is one path that terminates there, yes. And there are 2 paths that terminate here. So total of 3. So, and then at this 1, there's 1 path. There shouldn't be any paths here. Let me see. Maybe I'm at the wrong one. 0, 1, 1. -1, 0, 2, 0. Then -1, 0, 0, 1. There's one path here? Is there a path there? Yes, there is. Okay, yeah. 3 minus 1, yeah. Sorry. Then here, there are no paths. Yep. There is no path here. There's one path there. There are 4 paths here and 12 paths there. Let's see. At this 0, there are 4 on the left, 4 on the right. Yes. And at this 1, I'm guessing this 1 is a mistake then. This 1 should have 5, maybe? 5 paths instead of 4. Where's the 5th path? So there's 1 here. 2. So that's accounted for here. 3. and 4. Let me write this down and I'll be back. Alright, so the main changes here that I've made are as follows. So here, what I've essentially done is changed it so that for each item within the hash map, when we calculate a new sum, we will simply take the number of paths that we could use to create the previous value and set that as number of paths that we can create our new value. This is pretty straightforward because for each path that could create some previous value, as long as it goes through our node and when it goes through our node, all of those paths are valid to create that new sum value, no matter how many paths before can create the previous amount. Secondly, I also had to add a little bit of an overflow and underflow protection here. That's just because of the test cases, but that's mainly just there to make sure that things work as they should. The solution isn't particularly fast or particularly space efficient, but I think it works well enough, and I think that it's within the range of what is necessary, though I'll definitely have to check the solutions from other people after this video. So the main idea here is that we start at pretty much all the node values, and we keep a track of what is a kind of like a prefix sum. We keep track of how many times we've seen each individual sum value, and of course we only add into our next hash map that we pass into our children what is possible, so either starting at our current value or continuing the chain from elsewhere. Both of those are very much valid. We will go through all of the nodes, checking to see if they create a particular value with our target sum, and if it does, then we will return that amount. We do this top down, and then we make the recursive calls top down, and then we return from each of our leaves layer by layer, sort of all the way up until we get to the root, at which point we return our result. In any case, I hope you learned something, and I'll see you for the next problem.